go through and kind of compare and contrast the 4 mechanisms that we've looked at so far between chapter 7 and 8. So our 2 substitution reactions, so SN2 and SN1, and then our 2 elimination reactions, E2 and E1. Eventually, what we want to be able to do is, given a set of reagents, what type of mechanism is it going to go through? So if I give you an alkyl halide and then something that's nucleophilic or basic or both, what reaction or reactions are we going to write for it? I do have this handout posted under the Chapter 8 modules, so if you have a printer and want to print it, that would be cool. You can fill it out with me. If not, you can just sketch this on paper. But we're going to look at the reaction order. I'm just reading down the first column here. The rate law, mechanism, reaction diagram, stereochemistry, rearrangements, are they possible, substrate, the nucleophile and the solvent. So kind of what's going to dictate which type of mechanism. So if you need to sketch this on paper, you might want to just pause for a minute and make yourself a little table, or go print it, whatever you prefer, and then come back and we'll start filling it out. Okay, so hopefully you guys are ready to go. So remember, for reaction order, if the 2 is in the name, that means it's bimolecular, so it's second order. So the SN2 is our second order substitution mechanism. And then SN1 is going to be first order. And then the same thing for the eliminations. I'm going to scroll down here. E2, because the 2 is in there, it's bimolecular, which means it's second order. And then E1 is first order. That one's pretty easy because it tells us right in the name what order it is, right? The 2, those are our second order reactions. The 1, those are our first order reactions. Second order rate laws, remember, depend on the concentration of 2 things. So when I write my rate law for this one, rate, lowercase k is my rate constant, and then the concentration of my alkyl halide multiplied by the concentration of my nucleophile. First order, my rate depends on the concentration of 1 thing, so just the concentration of my alkyl halide. I'm going to see the substitutions through to the end of this table, and then we'll go back and do the eliminations. Mechanism, so remember, the mechanism for my SN2 reaction is concerted. It's going to be the same thing with E2, right? It's happening all in one step. So if I draw an alkyl halide on here, I'm just going to use X, and let's actually move it a little bit more towards the middle. I really didn't give us a ton of room here. And then I have my nucleophile, and what's going to happen is that nucleophile is going to add at the same time that leaving group is leaving, right? And because of that, remember, we have to do that backside attack. Right? They both can't come and go from the same side because those electron fields are going to, kind of run into each other, for lack of a better way of saying it. So when I draw my transition state, which I do want to see for this one, we need to make sure that that nucleophile and that leaving group, to make that a little smaller to make it fit, are going to be completely on the opposite side of each other. So dotted lines for everything that's forming and breaking. So we're forming the bond between the nucleophile and the carbon, so it's dotted. Breaking the bond between the carbon and the halogen, so also dotted. And then get everything else on here. We put brackets and that little double dagger symbol to show that it is a transition state. And then I guess my product goes down here. I now have a nucleophile on there. So remember, in that transition state, kind of a note you might want to write on there, that the nucleophile and the leaving group need to be 180 degrees, right? If I have one coming in from the left and the other going out from the right, if you wanted to do top and bottom, that's fine. If you even wanted to angle it, we'll sketch it over here real quick. If I wanted the nucleophile here, then the halogen needs to be there. They need to be straight across, however you want to do it. It doesn't really matter, as long as you draw that dotted line between the nucleophile and that halogen 180 degrees from each other. So make sure you get that backside attack. That's important. So I do grade on that when I'm grading this mechanism. The mechanism for our SN1 reaction then, because it's first order and there's only one thing involved in the rate determining step, I'm going to need 2 steps to get everything in there. So my first step, my halogen is going to leave. So my leaving group leaves. And it takes those electrons with it. So make sure the arrow goes to the halogen, not flying off into space somewhere. I'm then going to go through a carbocation intermediate. Because I have an intermediate, do watch out for rearrangements. And then from a stereochemistry standpoint, that intermediate is planar. So this halogen can add from either side, and I'll write those notes on there in a minute. Because of that, we can get a mixture of stereochemical products. I didn't give you perspective on the reactant, so I don't know what the stereochemistry was, but if it was chi, I remember we could get both. And maybe, honestly, we should go back and draw that. Let's add that stuff in. So let's have this coming out at us. Ooh, that's ugly. Ah, sorry, guys. It was getting too ugly anyway. It just needed to be redrawn. So I have that halogen coming out. Get that arrow back on there. Which means in my product, and I can do this a couple different ways, I can just write plus minus, meaning I'm getting both of them. What that means is I have the product where the nucleophile is coming out at us. I also have the product where that nucleophile is going back behind, because my intermediate is planar, right? Planar intermediate. So nucleophile can add from either side. So it can be coming out or it can be going back depending on what side it adds from. And if I don't have anything next door blocking one of the sides, it actually does add to both sides, so I get that racemic mixture. If we go back and add perspective to this one, we'll make the halogen coming out again, which means in my product, see if I can just erase what I want to erase. That nucleophile is going back behind. Because my configuration is inverted. And we'll write that down in the stereochemistry section here in a few minutes. So again, SN2, it's concerted. It takes place in one step. Nucleophile adds at the same time that that leaving group leaves. So I end up with an inversion of configuration. In fact, let's just write it. Inversion. And again, that's if chiral. For my first order reaction, right, my SN1, because that leaving group is leaving, I'm going through that planar intermediate. My nucleophile can add both ways. So we actually get a mixture of stereoisomers. We could say we get retention and inversion. Right? By intention, I mean it's retention, I mean it's the same as it was when we started. Inversion, this bigger, sorry guys, this is a little, by inversion, that's an and, I mean that I'm getting the opposite. So we're getting both the same configuration that we started with, and then the inverted product. Maybe we'll just make this a little bit bigger here. With the SN2, only inversion. So if it was R, it's S when we're done. If it started out as S, it's R when we're done because of that backside attack. Let's add the rearrangement part next too. Because I'm not going through a carbocation intermediate for SN2, there's no rearrangements. Because I'm going through a carbocation intermediate for SN1, there is that possibility. So under rearrangements here, I mean carbocation rearrangements. That's specifically what we're talking about. So possible. So both hydride shifts, that's more common. We could have alkyl shifts, not very common. But we could also have resonance. So watch out for that. If I give you something that's allelic or a benzylic, allelic or benzylic, there is that possibility of resonance. So do watch out for those. So let's go back up and get our diagram in here. So reaction progress, my energy, because this is concerted, it just takes place in one step. So no intermediate. Right, I have my reactants, my products, my transition state. We can add our energy to it. So my activation energy, and then my overall energy change. I'm going to put delta G, but if you use delta H, I'm fine with that. For my SN1, because this is taking place in 2 steps, I'm going to have 2 steps. So energy, my reaction. So we're going to go up. We're going to dip down for intermediate. So we're going to go up again and then come down to my products. I knew that was going to happen. I just wanted to erase part of it because I didn't come down quite low enough. But so up, but dip down to the intermediate, up again, and then down to our products. So labeling these guys, I have a reactant. I have 2 transition states. Even though we're not drawing a transition state for that mechanism, that doesn't mean I don't have them, right? Every time a bond breaks and forms, I have that transition state where those are partial. So do be careful for that. A lot of times like, well, there's no transition state. No, you're just not drawing the transition state. There still is one. So I have 2 activation energies on this one for my first step, and then one for my second step. And then my overall energy change is still the difference between reactants and products. When you draw it, and I almost goofed this one up, not even really thinking about it, make sure that your first activation energy is bigger than your second, right? Our first step is our rate determining step. So do make sure that EA1 is greater than EA2, right? The bigger the activation energy, the slowest step. The first step is my slowest step. It's the rate determining step, so it needs to have the bigger activation energy when you draw this. Okay, substrate. So I like to think about the mechanism when I'm determining the substrate. It just helps me remember if I think about what's going on. So going back up and looking at the mechanism here for SN2, because that nucleophile and the leaving group are both there at the same time, if you look at that transition state, there's a lot of stuff going on in that carbon. Because there's so much going on, it's going to be faster when it's less sterically hindered. So if we have less carbon-based groups on that alpha carbon, right, the carbon that the nucleophile is attacking, it's going to be faster. So methyl is going to be better than primary alkyl halides, which is better than secondary, and that's way, way better than tertiary. In fact, usually I just do that. So tertiary, generally not going to happen. We want less sterically hindered substrates. I wonder if we can write that in there. Less, I don't know if you guys will be able to see this in the video or not. Less sterically, it's a little hindered. So less sterically hindered is what I wrote if you can't read it. For our SN1, because it's going through that carbocation intermediate, the more stable that intermediate is, the better. More substituted intermediates are more stable. So for this one, tertiary is better than secondary, which is better than primary, which is much, much better than methyl. In fact, for this one, we can just kind of cross those two out. Just do be careful. Something at first glance might look primary, but if you can do some sort of rearrangement, or if it's actually allylic and not primary, be careful. It's still going to go. So I'm crossing it out, but again, if you can make that intermediate more stable, then it's still a possibility. So carbocation stability is the factor here. I keep switching colors here. We do want to remember that allylic and benzylic are also good. Allylic and benzylic good. You can put those right up with tertiary as far as how good they are. So I'm just going to make it a little bigger here. So if you can't see it very well, you can get it written down. So tertiary, secondary, those are good. Allylic and benzylic are also good. Primary, not great. If it's just straight primary, probably not going to happen. But if it has a rearrangement that makes the intermediate more stable, then it's still a possibility. If it's allylic, it often looks primary at first glance, but it's not. It has a resonance stabilization, so that's still good. So be careful for that one. Methyl, just, yeah, no, not good. Okay. Get this back to a normal size for you. Stop banging stuff around. So, nucleophile. The nucleophile is part of my rate determining step. So we want a good nucleophile. And that good nucleophile is generally going to be a charged nucleophile. So something like SH minus versus H2S. So charged nucleophile. Do remember though, a lot of times I'm going to give you a cation with it. So be careful. If I give you a metal and then our nucleophile, that cation has a positive charge, so my nucleophile is charged. So just watch out for that. Over here under SN1, a weak nucleophile is fine. It can be neutral, so something like water would be perfect for that. Right? If we go back up to the rate law here, if I look at this, my nucleophile is not part of it. So a weak nucleophile is fine. That usually means it's neutral. I will give you a list after we go through the elimination part of this, where we kind of compare and contrast nucleophiles to bases, because I'm going to say if it's a better base than it is nucleophile, it's going to eliminate, and we need to be able to differentiate from that. So I'll give us a list after we get through all four of these tables. Solvent, we want polar aprotic. Remember, if it's protic, it's actually going to stabilize anions pretty good. So it's going to stabilize my nucleophile. My nucleophile is my reactant. My reactant is more stable, it's less reactive. So we don't want to stabilize my reactant. So polar aprotic solvents are what we want. And then over on our SN, one side, we want polar protic solvents. That's going to stabilize my intermediate. The intermediate is the product of my rate determining step. So we're stabilizing the product, that's a good thing. So we're going to start going through the elimination portion of this. So we already started filling out the order. So remember the 2 in E2, it stands for bimolecular, so it's second order. The 1, first order. So we have the order already. I did notice down here I wrote nucleophile. I'm actually going to change it to base. I actually learned it as nucleophile for both of them, but we are going to differentiate between a base and a nucleophile. Remember we had said the nucleophile is actually going to attack. We can draw a little picture here. So if I have a halogen here, and then I'm going to draw a hydrogen out just to differentiate between the two. A nucleophile is going to add to that carbon. Remember that carbon is partial positive because of its polar bond to that halogen. So a nucleophile is going to attack the carbon. A base is going to attack that hydrogen. They both are nucleophilic, right? Both of them are providing the electrons, right? Our electron rich guy is our nucleophile, right? They're both nucleophilic. So I'm using the word nucleophile kind of more as a noun, right? It's going to attack that carbon. And then when I say base, I'm talking about something that is nucleophilic, but it's attacking the proton instead of the carbon. So just, you know, when I'm talking to elimination, I'm probably going to use the word base instead. I'm trying to get in that habit anyway. So I did change that column on you, or that title. Rate law, because it's second order again, remember that means that the rate depends on the concentration of two things, so alkyl halide, and then I'm going to put a B for base. If you put NU for nucleophile, that's perfectly fine. E1 rate, it only depends on the concentration of one thing, my alkyl halide being that thing, and then just remember, this is the same rate law as SN1. If I look at E2, because I'm putting base in there instead of nucleophile, it's not exactly the same rate law. It's still second order, still depends on the concentration of two things, but if my nucleophile would rather grab the proton, right, if it's acting like a base, then E2. If it's going to attack that carbon, then SN2. With my elimination, my E1, right, my unimolecular one, it is exactly the same rate law as SN1, right? That nucleophile or base are not involved in my rate determining step. My mechanism, second order, so it's still concerted. Everything's happening at one time. So stereochemistry is going to matter for this one. So my base, it's going to grab that proton at the same time those electrons that were bonded to that proton are going down to form my new pi bond, and then my leaving group is going to leave. Because that's happening at the same time, it does need to follow anti-periplanar or anti-coplanar geometry. We can go add that down to our list here. So anti-coplanar, anti-periplanar, same thing. Honestly, if it's anti, they have to be in the same plane, otherwise they wouldn't be anti. So I have my hydrogen going straight up, I have my halogen going straight down. So they're both in the plane of my iPad, but they're anti to each other. One's up, one's down. If I wanted to have the hydrogen going back, then I would have to have the halogen coming out. So the two need to be anti to each other. Because it's concerted, I do want to see the mechanism. So, or sorry, not the mechanism. I do want to see the transition state. I always want to see the mechanism. So I am going to focus. That's drawn kind of ugly. Let's redo that there. Try to redo it. Maybe I'll draw out those two carbons. I don't know. I'm not sure what's easier. Sometimes when I draw the carbons and then I do everything else skeletal, it's kind of confusing. But we're breaking that bond. I am forming a bond between the base and that halogen. Sorry. I want to be able to put the brackets around if you're wondering why I'm erasing it and moving it over. And the way I had it over there, I wouldn't have room for it. So that's my base. So the base is taking the proton, so I'm forming that bond, so dotted. The bond between the proton and the carbon is being broken, so dotted. I am forming a pi bond, so I'm going to have a dotted line there. And then my leaving group, my halogen is leaving, so a dotted line to that. And then don't forget the other carbons. And then it's a transition state, so brackets and my double dagger sign. And then my product, I have that new pi bond. Remember, elimination reactions, we're adding a pi bond. So anti-periplanar geometry, that's happening at the same time. And then our product, and this is going to be true for both of them, so we can put it over here. Both are going to follow Zaysev's rule. And that's regiochemistry. So stereochemistry, right, it's how they differ in three-dimensional space. So regiochemistry is what region of the molecule are we going to eliminate. So both beta carbons, remember beta carbon is one carbon away from where my halogen is. So I'm just going to go back down here and sketch it again. If this is my halogen, right, that's my alpha carbon. And then one carbon away, that's beta, and that's beta. So it's a beta elimination, and alpha beta elimination is the type of reaction. And I do have two options. I can take that hydrogen off, right? There are two there, but we're only going to remove one. There's 3 on my other beta hydrogen. I could take, I'm just going to draw one because we're only going to lose one, but there are 2 others on there. The one that it would lose, however, is the one that's anti to that halogen. So we actually have 2 options. So we'll call this hydrogen 1. We'll call this hydrogen 2. So if I removed hydrogen 1, I get that product. If I remove hydrogen 2, I get this product. And we actually do get both of them because they're both possibilities. It's just that we're going to get more of one than the other. The one that we're going to get more of is our more substituted alkene. That's what Zaysev's rule is telling me. So this is my major product, meaning that most of it is in that form. This is my minor product. And I did say this on a previous video, unless I specifically say draw all possible products, the only one that I'm looking for is the major product. If you actually draw only the minor product, I'll take off some because you're not, like, I don't know that you know that it's the minor product, right? You're not following Zaysev's rule. If you want to draw both of them, that's fine, but you're going to need to label which one's major and minor because, again, I don't know that you know that you need to follow Zaysev's rule. So unless I say draw all possible products, you need to draw major. If you draw both, make sure you tell me which one's the major products. I need to know that you know that. So if we go back up here, never finished writing rule, both follow Zaysev's rule. So do watch out for that. So the more substituted product is the one that we want. That's our more stable alkene. If I look at my mechanism for E1, let's make this a little bigger again. The first step is the exact same first step that we had with SN1. My leaving group is going to leave. And I go through that carbocation intermediate. My next step, now my base is going to come in. And it's going to take that proton, and then those electrons are going to go down. And then I'm going to get that alkene. Again, I could take the beta carbon, I could take the hydrogen off the other beta carbon, but I want to follow Zaysev's rule. So some special notes, right? First step is the same as with SN1. The reason that's important is oftentimes if something's going to go E1, it will also go SN1, and you'll get both of those products. So watch out for that. So anti-coplanar, we did write that below, but we'll put it up here also, so be careful for that. I do have rearrangements with E1, that's possible. Let's add that. So possible. Anytime you have a carbocation, watch out for rearrangements, right? And then the same options. We could have hydride, alkyl. Alkyl's pretty rare, but it is possible. Alkyl shifts. And then also resonance. If it's allelic or benzylic, so watch out for those guys. Make it smaller again. Don't make you guys dizzy when I zoom in and zoom out so much. No specific stereochemistry for this one. right? I'm not eliminating the hydrogen and the halogen at the same time, so the whole anticoplanar thing is not going to apply to it. Oh, we should add, if it's under the E2 section, remember if it is cyclohexane, it's in that chair conformation, and it needs to be diaxial. So trans diaxial, that's an A. So if it's, let's try to write that a little neater. If it's cyclic, a cyclic hexane, trans diaxial. So that should go in the stereochemistry space also, however you can fit it in there. So remember that the hydrogen and the halogen need to both be in the axial position, and they need to be trans to each other. That sometimes then dictates the regiochemistry. You might not actually be able to form the most substituted product because this elimination is going to override that. It needs to eliminate in that orientation. And I did give you an example in the previous video on that. Rearrangements, nope. There's no carbocation. You can't have carbocation rearrangements, right? It's a concerted. Okay. Energy diagram, they're going to look very similar to their second order and first order substitution counterparts. Again, it's concerted, so one step. We go up to our transition state and then down to our product. So reactant, transition state, and product. Activation energies. I'm losing my voice. And my product. Delta G, delta H, whichever. This one does take place in 2 steps, so same sort of idea. I'm going up to transition state. I have a dip for an intermediate, and then down to my product. So reactants, transition state, product, and then my intermediate. I don't remember if I drew the intermediate on the last one. Yeah, I didn't. Sorry, guys. C+. Don't forget that guy. Or I for intermediate. It's just we know that specifically it is a carbocation intermediate, so that's why I'm drawing it that way. 2 activation energies. EA1, EA2, and just like before, by before I mean the SN1 reactions, my first activation energy needs to be greater than my second. It's the slowest step of my mechanism, right? It's the rate determining step. And then my product, so delta G. So those look very similar, if not the same. They are the same as my substitution ones. Substrate, tertiary. This is the one that most people get mixed up. So because the SN2 primary is better, right? We want the least hindered substrate, right? The nucleophiles trying to fit into that alpha, onto that alpha carbon, and everything needs to be there. Here, the hydrogen's hanging off the side, so it's okay. Like, steric hindrance isn't the overriding factor. What the factor is that my transition state looks kind of like my alkene. And remember, more substituted alkenes are more stable, so the more substituted that transition state is, the more alkene looking, right? The closer it is to the product, the more stable it is. If that makes any sense at all. It probably didn't. And then this one, I'm going through like carbocation. So, and then we also know that allylic and benzylic are good. The only one of these 4 mechanisms that are favoring primary, if we go back up, the only one that are primary is better is my SN2 mechanism. So nucleophile, remember we changed that to a base. We're taking the proton. So it is nucleophilic, it's the electron rich one, right? It's the one that kind of my electron source, but it's taking the proton. So if you think Bronsted-Lowry, it's a proton acceptor. It's really a proton taker, but I am using the word base there. So strong bases, and then also bulky bases. So things that are sterically hindered, strong, bulky bases. If you see a strong bulky base, always E2. Don't even think about anything else. Just see that base and think E2. So if I give you this alkyl halide and then NaO and that, E2, right? Sodium I don't care about, right? Na plus. And then this guy, there's a carbon in there. So I have an oxygen with like a T-butyl group bonded to it. That's big, right? I'm drawing it in skeletal structures, but that's a carbon all with its 3 hydrogens. And then like we'd say this one's coming forward, this one's going back. And it has its 3 hydrogens. And then this is a carbon with its 3 hydrogens, right? That thing's bulky, it's sterically hindered. It's going to be a base. It's not going to be able to be a nucleophile. So even though it's charged, right? Let me redraw it here so it's not so messy. Even though it's charged, it's really tempting to look at it and say, okay, it's a good nucleophile, right? We said good nucleophiles were charged, and then this is secondary, and think, okay, it could go SN2 also. No. Big and bulky, right? If it's sterically hindered, that was one of our trends where basicity and nucleophilicity no longer coincide, right? If it's sterically hindered, it's going to be a stronger base than a nucleophile. Go back and look at that section if you have to, where the two things don't always coincide. So big, bulky, sterically hindered, bulky bases, right here, strong base, E2. If it's a strong base, let a base be a base, right? Bases are going to take those protons. So that's what's going to happen. So anytime, sorry for all the scrolling, if I'm given something like this, right away, E2. I don't even look at anything else. For E1, weak bases are fine. So we did weak nucleophiles up on the SN1 column. A lot of times a weak base is my weak nucleophile. Again, those two often compete with each other. We can get both. Under solvent, polar, aprotic, but also protic. Basically a wide variety of solvents. The solvent usually doesn't help us with this one very much. If it's a strong bulky base, or both, that's redundant, E2. I usually don't need the solvent to determine that one. But polar aprotic is good. Protic also works. Here we do want protic, polar protic. So my advice to you guys, now that you've done this with me, is to study it a little bit and then do it on your own. Make yourself a blank table or print out another copy and try to fill it in without looking at it. So it's kind of a really good test if you can be able to tell the difference. In our next video, we'll actually go through some examples.